Graph C has this equation. We're asked to find an expression for dy by dx. So we need to differentiate implicitly here. And the hardest term is going to be this one. But remember our inside-outside rule, we've got something to the power of 3. So we just deal with that first. It's going to become 3 times that bracket, so x plus y, and then we lower the power by 1. We just differentiate it as we would normally if it was x cubed, but keep the inside as it was. And then times by the derivative of the inside, which in this case is going to become 1 plus dy by dx. All right, got that sorted. Then we've got 6x minus 3 lots of dy by dx. And we're differentiating each term, and that minus 2 disappears. Okay, this is good. Gonna divide through by 3, it's like straight away. And then, right, do not expand the x plus y squared. Like you get away with it, but you're just overcomplicating if you do that. So I'm just going to do x plus y all squared times 1 plus x plus y all squared times dy by dx. Because remember, I'm trying to get dy by dx by itself, and that's going to equal 2x minus dy by dx. So let's get the dy by dx on the same side. It's going to be dy by dx plus x plus y squared dy by dx, and that's going to equal 2x minus x plus y squared. Factorize out the dy by dx, so we'll get a 1 plus x plus y all squared. And then I can divide through. And this is as neat as it's ever going to get. You know, expanding it, it's not going to cancel or anything. This is a solid answer. Now, we're told that the point P10 lies on C and asked to show the normal to C at P has this equation. So when x equals 1, we can work out, and y equals 0, we need both here. dy by dx is going to equal, and I just need to sub them in now, so I'm going to get 2 minus 1 squared, that's going to be 1, over the denominator, which is 1 plus 1 plus 0 squared, that's just going to be 2. So that is the gradient of the tangent at P. It's the instantaneous gradient at P, but that is equivalent to the gradient of the tangent. I've gone with that because then the normal gradient will be the negative reciprocal. So we've got some sort of curve, we've got the gradient of the tangent, so we've got a tangent here. Here's the normal. It's at right angles by definition to the tangent. So the normal gradient is therefore going to equal minus 2, the negative reciprocal. You just flip it around and then stick a negative in. The two of them must multiply to give minus 1. And now we can just sub in our point and the gradient. So y minus y1, y minus 0 is going to equal minus 2 times x minus x1. That's x minus 1. Y is going to equal minus 2x plus 2. And finally, we're asked to prove that the normal does not meet C again. It's going to meet the curve at P, but not anywhere else. So we've got our original curve, we've got the normal, let's solve them simultaneously. Now, it made sense to me to just sub y straight in, and I would do that every time, unless like you can sort of see immediately that putting x in would be easier. Putting x in seemed to be more difficult because I'm going to be like minusing 2 and then dividing by minus 2. I've got a fraction. But it turns out that if you substitute in for x, you get a slightly easier quadratic. I'll let you look into that if you want. Like I just wouldn't have, thought to do that. And again, if this happened, I would straight away sub y in. So I'm going to replace all of these y's by minus 2x plus 2. It's still going to work out absolutely fine. So that will give me x minus 2x plus 2. I should probably actually add when C and the normal intersect, Don't forget, we're going to use this later on. We know that x equals 1 as a solution. Put that in brackets, we'll come back to that. That is going to be vital. X minus 2x plus 2 cubed is going to equal 3x squared minus 3 times minus 2x plus 2 minus 2. We've got an equation just in terms of x now. It's a cubic equation. We're going to get 2 minus x all cubed equals 3x squared plus 6x minus 6 minus 2. That's going to be minus 8. Okay, that's looking good. We're going to have to either do triple brackets to multiply this out or use the binomial expansion, or the quickest way is going to be Pascal's triangle. These are going to be my coefficients. So I'm going to get 2 cubed plus 3 times 2 squared times minus x plus 3 times 2 times minus x squared plus minus x cubed. And that again is going to equal 3x squared plus 6x minus 8. So that gives me 8 plus, or sorry, it's me minus 12x plus 6x squared minus x cubed, and that's going to equal 3x squared plus 6x minus 8. Let's sort this out. It's going to become x cubed, add that onto both sides, then 3x squared minus 6x squared is minus 3x squared, plus 12x to give plus 18x, and then I'm going to get a minus 16 equals 0. And I want to now solve this equation. Remember what I said, we know that x equals 1 is a solution. Let's just check, because if you made a mistake, you might be able to, well, hopefully be able to pick it up here, unless it's just so happens that you substitute 1 in and still get 0 despite your mistake. But if I substitute 1 in, I'm going to get 1 minus 3 plus 18 minus 16, and that is 19 minus 19. It is equal to 0, so that gives us a little bit of confidence. So we know that x minus 1 is a factor here. So you've got two options. You can either use polynomial division, or you could just go straight for it and see if you can factorize. We know we need x squared to get the x cubed. We know we need a plus 16 to get the minus 16 here. And then my x squared terms are going to come from here. I'm going to get minus x squared, and I need another minus 2x squared somehow to get the minus 3x squared. That is going to mean this one has to be minus 2x. And I've factorized it. Okay, that can be really quick. If you're a bit happier then to do this, then of course you can do polynomial division. I'll just remind you about that. There's different ways to do it. I always go with this way because it just extends really nicely to when you divide by higher powers. You just learn one rule. I know that there are quicker ways, or maybe ways that you're a little bit happier with, but this is a good method. So x is into x cubed gives us x squared, times back through, we get minus x squared there, subtract minus 2x squared plus 18x, divide the minus 2x squared by x, we get minus 2x, multiply back through. If you end up not getting a remainder of 0, you know you've made a mistake. Here, it's going to work out. So same factorization, right? So we know that x equals 1 is a solution. X equals 1 at p. Or it must be that x squared minus 2x plus 16 is equal to 0. But we're looking to show that actually this doesn't have any solutions. Let's look into the discriminant. B squared, you could complete the square and show it's always positive, but this is just going to be quicker, I think. B squared minus 4ac for this is going to equal 4 minus 64, which is less than 0. So no real solutions. And hence, that's enough. The normal will not meet the curve again. Okay, good question. Implicit differentiation, tricky to start it off. It wasn't like a show that question, so everything from then on relied on us. But if you get to this, you can be really confident, of course, with that first part. Then we substitute it back in. I substituted in for y. You could do x. Y just felt like the natural choice to avoid fractions. Got a cubic and then divided or factorized it to get this and showed that this part had no solutions. Well done.